Okay, so Elaine, please go ahead. Yeah.
Thanks. So hi everyone, my name is Elaine. I'm a graduate student at NYU, and today I will be telling you about synthesizing protocols from global multi-party session types. This talk is primarily based on work that was published at CAV last year that is joint work with Felix Stutz, my advisor Thomas Wies, and Damien Zufrey. Multi-party global types represent message passing concurrent protocols, such as this two-buyer protocol. So here we have 3 participants, 2 book buyers and 1 bookseller. So the protocol commences with one of the buyers sending a title to the bookseller. The seller will send a quote for this book back to each of the buyers. And now one of the buyers may propose a split to share the cost of the book with the other buyer. Now either this other buyer accepts the split and they both send their share to the bookseller, or they reject the split and send a no message to the first buyer, thus terminating the protocol. As we saw already, such global protocols are visualized as high-level message sequence charts, where the black boxes represent the control flow of the program, with arrows representing branching. The vertical lines represent the different roles participating. So here P is the bookseller, Q and R are the 2 book buyers, and the different colored arrows represent different message exchanges, with the double-lined boxes representing final states. So the grammar for these global types are defined inductively as follows. You have 1 constructor for termination, 2 for recursion, and 1 for communication events. In the communication events, there can be a choice, a non-deterministic choice, where the same sender can choose to send different messages to different participants. And we will look more at this construct later. So this is the type representation of the example protocol that we just saw. We interpret these global types asynchronously over networks with FIFO peer-to-peer channels. So we have this synchronous finite state representation of the protocol. This is basically a deterministic finite state machine that's labeled with synchronous communication actions. And this naturally defines a set of runs of such a state machine. So to get the asynchronous semantics, what we first do is we split each synchronous event where the send and the receive are coupled together into its send and receive asynchronous counterpart. So effectively doubling the length of this trace. And now in any execution that is the former, where you have this receive highlighted, a receive from Q as well as a send from P, if this is a trace in the network, then so too will the following be a trace in the network where these 2 independent events are interleaved in the trace. So the semantics of such a global type is the closure of all of these asynchronous traces under this indistinguishability relation to capture all of the possible interleavings in an asynchronous network. So to cast this in the language of terminology from earlier, by construction, the semantics we have here are 1 synchronizable and existentially sum 1 bounded, meaning that over all of the channels, you have configurations where there's at most 1 message. The implementation model that we adopt for these global types are communicating state machines, introduced by Brandon Zafiropoulos in 1983. These are a collection of DFAs that are pairwise connected by channels. So the configuration of such a CSM would contain 1 local state for each of the participating roles, in addition to the configuration of all of the pairwise message channels, the contents of which can be represented as a string of messages. So the question of realizability for these global types, which we call implementability, is for a given global type, whether there exists an implementation in the form of a communicating state machine, such that the language that is recognized by the communicating state machine matches the language that is specified by the global type. And in addition, we would like the communicating state machine to be deadlock-free. In these session type frameworks, the checking of implementability and the synthesis of such an implementation when it exists is typically done together via what is called a projection operator. So mathematically, a projection operator is a partial function from the set of global types to the set of CSM implementations. And a projection operator is sound when every implementation that it computes implements the global type correctly, and it is complete when every implementable global type will successfully have an implementation that's synthesized by this projection operator. For the longest time, the projection operators in the literature were sound but incomplete, and I'll give an overview of this history here. So this blue box here represents the space of all of the global types, of which the realizable or implementable ones are only a subset. In the initial paper that introduced multi-party session types, they were working with a more restricted fragment, where in the type specification, the choice can only be a sender sending the same recipient different messages. So it disallows sending different recipients different messages, which intuitively encourages more desynchronization in the protocol. This more expressive fragment was introduced in the Conquer paper 2021 generalizing projection. And so yes, in the original paper, they gave a projection operator that was linear in the size of the global type, but that was incomplete. With this generalization to a more permissive form of choice, this projection operator now became polynomial time, but was still incomplete in that it didn't precisely capture all of the implementable global types. There was an ECOOP paper in 2023 that reduced the problem of implementability for global types to the realizability problem for a fragment of high-level message sequence charts. However, this reduction required the assumption that every trace in the language, every prefix of a finite trace is also the prefix of, let me try that again. Every prefix of an infinite trace is the trace of a finite word in the language, meaning that this fragment rules out global types, for example, that contain only infinite words. And this projection that was implied by this reduction is in X space. And finally, last year, we gave the first projection operator that is both sound and complete, and we showed that this projection operator is in P space. And I just want to mention that outside of this fragment of global types that I was depicting, there have been a multitude of papers that study different extensions to the type syntax to model more communication features. So with these two original papers from 2008, there was then types that are parametric in the number of participants, that are multi-party. There are types that can contain infinite data. So these are expressed by data refinements. There were extensions that incorporated failures into the global specification. And there was also this somewhat confusingly titled paper that implemented an actually incomplete linear projection operator, but it precisely implemented this. So what all of these projection operators in these papers had in common was they utilized this syntactic linear projection operator. And next, we'll look at some examples to motivate exactly where the incompleteness of this style of synthesis comes from. So the first reason that these syntactic projections are incomplete is what we call syntactic brittleness. This basically corresponds to the fact that for a given global type, there may not be a unique syntactic representation. But because implementability is a language-based property, we would expect that for any syntactic type corresponding to the same language, that you get the same projectability. So in these two examples here, we have a type that's between three processes, and the type first branches into a left and right control flow path. In each of the paths, there is the same loop that then has the option to exit. So the only difference between these two depicted types here is that in the type on the right, in the right branch, in the left branch, I have unfolded one iteration of this loop, and afterwards I continue into the same loop. So it should be easy to see that these two types are describing the same asynchronous language. However, when we try to project these types using these syntactic linear projection operators, so what is done is basically a traversal of the type inductively. And for each action, we try to convert the global action into the corresponding local action and thus transform it into a local type. And what happens to the example on the right is that in order to form a coherent local type, you would need to merge in the same syntactic subterm a single communication event with a loop, which is disallowed by the syntax of local types. And so the protocol on the right would thus be rejected by these syntactic projection operators, even though the one on the left would be accepted and the language is thus implementable because they are the same. So now let's talk about a slightly more subtle reason why these syntactic projections fail. And this has to do with the fact that they are doing linear traversal in the global type. So let's look at this example with a bit more detail. In this protocol, we have again 3 participants, P, Q, and R. And the protocol commences by P making a choice to send either an orange or a purple message to Q. If it sends an orange message to Q, Q will forward this message to R. And if it sends the purple message, then Q will do nothing. And after these communications, the protocol enters into the same loop on the left and right side. And in the loop, what happens is P again sends an orange message to Q, and Q will forward this orange message twice to R. So this loop is carried out an arbitrary number of times, and at some point P can decide to exit the loop, and it signals this by sending a blue message to Q in the bottom 2 boxes. Once Q receives this blue message, signal of termination, it will forward the signal to R. And at the very end of the protocol, R must send a message back to P that corresponds to the choice that P initially took in sending either an orange or a purple message to Q. So let's look at the implementations for this example that we suggestively call the odd-even example. So in this protocol, it is clear that P is the choice maker. P dictates the control flow. It initially chooses whether to take the left or the right branch. It chooses how many times to carry out the loop, and it sends the termination message that is then transmitted to the other participants. So the implementation for P, the DFA for P, is very similar in structure to the global specification. Now for Q, Q does not make the choices, but Q is P's right-hand man. So anytime P makes a choice, Q learns about it immediately. So the structure of Q's implementation is also straightforward and similar to the structure of the global type. The only difference is that in the 2 branches, Q is performing the same actions, so they get collapsed to this triangle cycle over here. Now onto the implementation for R. So R is neither making the choices nor learning about the choices from P. So in fact, it looks like R is doing the same actions on both of the branches. All that R is ever doing is receiving these orange messages from Q. But somehow at the very end of the protocol, R needs to, in order to correctly follow the protocol, send the right color message that indicates it actually knew which branch was being taken despite not being explicitly informed. We claim that this protocol is actually implementable also for R, and the way that R can detect which of the branches was taken is by tracking the parity of the number of orange messages that it receives from Q. So if P took the left branch, at the end of the protocol, when R receives the blue message, it will have received an odd number of orange messages. Whereas if P took the right branch, it will have received an even number of orange messages. So these transitions that are highlighted in yellow represent R updating its belief on which branch was taken by P each time it receives an orange message.
Wouldn't be simpler to add one bit of information so that P tells Q which branch has been taken and Q tells R and informs?
Yes, so that would also result in a implementable protocol. But sort of this slightly contrived example is to demonstrate that
of course
these choices can often be inferred without explicit communication.
I mean, the difference is that if you add one bit of information, I mean, the decision problem gets much more difficult because you don't know how much information you are supposed to add in order to make it work.
Yes.
Okay, thanks.
Right. So these critical transitions that flip between odd and even numbers of messages that are required for the implementation, the synthesized implementation to be correct, cannot be computed by any projection that is linear in the size of this global type specification. So now we'll describe this sound incomplete projection operator and see why it fills this completeness gap. So the first thing that we did was to actually separate the synthesis and the checking of implementability into two separate questions. And the synthesis step, as was alluded to earlier, is actually very straightforward because the global language already specifies a local language for each of the roles. What you can do is just project away the behaviors that are not related to a certain role. And so you start with this global state machine. You erase the behaviors that the role is not involved in. For the behaviors it is involved in, you project it to either the send event or the receive event, depending on what it's doing. These epsilons now introduce non-determinism, so you determinize this NFA and you get a DFA for each of the roles. And the property you get from this is that the language each of these implementations individually recognizes is going to be exactly the language of the global specification when you erase all of its irrelevant actions. So you can always synthesize such an implementation, right? This will always be fine. However, you may have noticed that this synthesis sort of has nothing to do with whether this initial global type is implementable or not. So the difficulty comes in actually checking whether these implementations will compose together to satisfy implementability, meaning that they will recognize the exact same language and also be deadlock free. In the checking implementability step, we then have an algorithm that checks these synthesized candidate implementations directly. And we have two conditions that are checked on respectively the send and receive transitions that appear in each role's DFA. So to give a motivation of what each of these conditions are checking, for send events, let's consider this pair of protocols here. So in both of them, again, P makes a choice to send either an orange or purple message. In the top choice, in the top protocol, regardless of what P sends to Q, R will send the same blue message back to Q. So intuitively, R does not need to know what choice it was. It will just send a blue message and terminate. Whereas in the bottom protocol, the type says, well, you have to match the color of the message that P sent to Q, even though you don't know it. So any implementation for R that is able to generate all of the behaviors contained in the global specification must additionally generate some behaviors that are not in the specification and thus violate implementability. In particular, when, for example, P sends the orange message and it doesn't know, then it may send the purple message and thus result in a trace that is not contained in the language. So intuitively, the send condition enforces that if you don't know what state you're in, any send that you can fire has to be permissible from all of the states. And these states here are states in the subset construction, so these are directly global states. So you can check this locally on the subset construction. For receive, the story is slightly different. So again, we have here a pair of global types. P again sends either an orange or purple message to Q, indicating the choice. In the bottom protocol, Q must receive first, and then Q sends and P sends a orange message again to R. So again, R does not know about the choice. In the bottom protocol, the order in which R receives these messages from P and Q has to correspond with the choice that P made. So if P took the top branch, R must first receive from Q and then from P. And if P took the bottom branch, R has to receive in the opposite order. And because we have FIFO peer-to-peer implementation model, both of these messages can arrive and be available for R to receive at the same time. And thus, likewise, we can construct error traces where R receives in an order that is mismatched from the order that P intends. So what we've described is this algorithm that operates directly on the candidate implementations, which can always be computed. And because you need to determinize these NFAs, this results in a P-space synthesis algorithm. What you can do is also to check implementability directly on the global type before synthesizing implementations. And if you do this directly on the global type, the algorithm is in polynomial time in the size of the global type. And the reason for this intuitively is that you only need to relate pairs of global states. You never need to possibly relate n of them, where n is the size of the global type. So in summary, I have presented and contrasted two approaches to synthesis for these global types: the syntactic and linear incomplete approach versus a more automata-theoretic approach that gives you completeness. And I have described the complexity for this new projection operator. Some other results that we have worked on in the multi-party session type space relate to subtyping. So there are many variants of the subtyping problem. You can ask whether you can sort of wholesale replace the entire CSM and ask whether this implements a subset of the behaviors, or you can impose some assumptions on n-1 roles and say, can I replace the DFA for one role with a different one? And for this, you can refer to our ESOP paper earlier this year. What we are currently working on is extending the fragment of global types to express more protocols. So this largely falls into two directions. We are working on adding predicates that basically allow the underlying state transition system to be infinite state. So either you can have registers in your state that store the value of variables that can be referred to later on in the type, or you can send infinitely many values that are represented symbolically as a predicate. So this is one direction. Another direction is we actually realized that for the syntax of these global types, they sort of define only a very restricted class of DFAs. For example, final states are not allowed to have outgoing transitions in the DFAs that are described by these syntactic global types. But actually, our implementability result can also apply to more general DFAs where this restriction is lifted. One important restriction that cannot be lifted is that in this non-deterministic choice, it still has to be one sender sending messages to different recipients. You cannot have different senders sending different messages. And this is allowed in the more general message sequence chart case, and this is the reason that realizability in that setting is undecidable because of this mixed choice construct. So within the space of infinite state specifications as global types, we are also identifying fragments that are effectively decidable for implementability. The synthesis problem remains largely the same, which is you basically synthesize a language equality preserving implementation, and then you're good. So yeah, that's all that I have for today. Thank you for your attention, and I'm happy to take any questions.
Are there some questions?
So I was wondering how this how does it compare to something that we did a long time ago called local choice implementations? So there was a condition on high-level message sequence graphs to be local choice, and then we got implementations that were deadlock free because the choice, I mean, was decided always locally by some process, but with adding some again, with the same paradigm of having implementations where you, in comparing with a message sequence graph, you can add some information in the messages. So you can put something to declare what is the choice actually, which branch to take. So how does this compare to this local choice?
Are these high-level message sequence charts or just MSCs, like finite MSCs?
So this high-level, so it's exactly these graphs with nodes labeled by finite MSCs.
Okay, so loops are allowed as well then.
And loops are allowed. And local choice meant something that on each branch, so that there should be one process that decides about the branching. So, and then other processes learn about it because there were some causalities. So, I mean, the definition is a bit more complicated, but do you know this work or?
I'm not sure which paper it is you're referring to.
Long time ago, 2002. ICAF 2002, no.
Maybe not.
Okay, so we can discuss about this afterwards.
It's local choice. If you don't, so this MSC graphs impose some conditions, synchronization conditions that are not visible immediately because you have this choice that is exactly not local choice. Maybe you can go back to several slides like this. No, so in what sense? And there is another problem, like a question. I don't understand exactly what is implementability. So in what sense, for example, the first box on the top with 2 arrows is implementable? Because you ask for blue arrow. No, but implementable means that the projection is the same? So
No, implementable just mean there exists a CSM that will implement this.
but you need to enforce that orange message arrives before a blue message.
Yes.
Okay, so this is synchronization of this. Okay, but then so then back. If you don't have a local choice, so you don't know whether you go left or right, how do you implement this?
Do you mean for which role are you talking about?
For here it's you don't all your examples had local choice, so I don't have the. Yes, no.
Local choice would be that the left role would inform the middle and the right one about the branch. Yeah, but here you don't have it. But it happens so that the right role is innocuous to the choice.
Okay. It's more. Okay, maybe then later.
Okay, so that's the right point. Let's kind of stop now, go for a break, and whoever has a question can still ask Elaine questions in the break. So let's thank her once again.